supposedly the time rate of change of the energy of the system itself. Now, I don't think anyone is going to argue that energy is not conserved. Of course, Niels Bohr thought that for some period, but then like the neutrino was discovered and everything was fine again. So I think we really do believe that this is not a Rosetta Stone for creating energy out of nothing. But we usually describe the total energy then as the sum of chemical energy, i.e. material energy, and nuclear energy. And it's been suggested, of course, that the nucleus, the nuclei are playing a special role in this particular system. If we just insert these expressions, the energy out is the energy in plus the energy given up by the chemical energy plus the energy given up by the nuclear system. Everybody agrees, no problem. Now it's the next line or two that makes some problems. One group argues that since the chemical energy can be estimated to be only about 10% of the extra energy that is out versus in, it must be that that missing energy, 90%, is made up by something else, and what else is there but the nuclear reactions? Of course, 0.01 isn't given with a great degree of certainty or uncertainty, and there's always some possible error. The second group would say, well, look, we know that the nuclear energy, depending upon what you believe the total rate of particle production, whether it's neutrons or charged particles, gammas, what have you, is something of order 10 to the minus 13th of the observed excess energy of production. And therefore, it's really obvious that the nuclear cannot produce the missing energy, and it must be, therefore, the chemical, but those poor chemists can't calculate well, or they're missing a little bit of the energy in the basket. And of course, the most exciting possibility is that, of course, this bottom line is in error, that we really have something much larger than 10 to the minus 13th, and the nuclear people are missing something. But that's one of the big debates. So the energy debate is, I think, continuing. My own contacts around suggest that most of the people that I communicate with believe that this cannot account for the missing energy. It's indeed a very interesting and fundamental phenomena, but it is not the phenomena that's connected with the so-called missing energy. I was very pleased to hear that the Stanford group feels that it is now seen not only excess power output, but excess energy output, and those two are very different. I think each of us knows how our battery works in the car. We charge it slowly for a long period of time, and then we get a lot of energy out over a short period of time. The fact that it produces energy which corresponds to 100 or 200 amps while you charge it at 1 amp doesn't mean that there's a nuclear reaction taking place. I've heard other descriptions about a cow drinking ice water and relieving itself at a very different temperature, but that's not a nuclear reaction. But this proves nothing. This is a different system. Now, just to illustrate what we're talking about here, consider a light bulb, a 100-watt light bulb, and you view it at 1 foot, and if you take the solid angle subtended by an eye wide open, you probably get about 1 watt into your eye. If you get 10 to the minus 13th watts, that corresponds to the same light bulb at 5 miles, plus or minus a mile. So what we're trying to do is say that somehow the light bulb, which has plenty of energy to explain the excess heat, may be somewhat uncertain in its effective position. Maybe it's at a half a foot or a quarter of a foot, and that could explain everything. While here you've got to move the light bulb from 5 miles down to a half a foot. So that's another way of accounting for the difficulty of making nuclear physics work here. So that's one point. The question is, energy, is it chemical or nuclear, or what ratio? The second issue, I think, is this non-reproducibility that Norman was talking about. Every field, when it gets started, has many, many phenomena to sort out relative to the fundamental issues. And I've been working in high TC superconductivity for a couple of years, and that has certainly been the situation there. Fortunately, things are getting in much better shape. And many theorists are now looking for another field because they have published a whole series of papers which are thrown out once the materials get under control. When we think back to the semiconductor period of the 30s, when the semiconductors were in terrible condition, and then in the 40s we know that zone refining, many things came along, and semiconductors are now well under control, and they are real phenomena. So hopefully over the next month, through information exchange, sample exchange, as Norman suggested, maybe a more structured situation, the reality and reproducibility of the experiments can be greatly improved so we can really deal with the difficult problems rather than only the confusing problems. Now, reading a little bit through the notes I had and prepared by some friends I'll mention in just a moment, there are a number of really fascinating results presented here. One is the highest rate of neutron production, which is something like 2 × 10⁻22 per pair of deuterium per second, while the lowest upper limit, i.e. we saw nothing, but we could have seen something if it was below this upper limit, was about 10⁻25. That is, there are around 4 orders of magnitude variation from the highest observed to the lowest non-observed limit. Now you might say these down here didn't see anything because they were using the wrong specimens. As you remember, Jay Rhine also had these sorts of arguments. Why can you not see what's on the cards of a person hiding them at the other end of the room? It's because you're not sensitive to that. But there may be something very fundamental here. I must say I personally am rather optimistic that this phenomena is real, and it's quite real at this level of 10⁻20 something. It'll be a real shame if this goes away. Who knows, but we'll have to wait. I should also say, of course, that I do believe that excess heat is produced. I think there are very good people at making calorimetric measurements. It's the origin of that heat, of course, is what's at debate. Now, there's an enormous effort having gone on in a room 5 over the past few days, making a database. And at 1:30 in the morning in my hotel, the database was presented to the night porter, and I picked it up to draw these transparencies. This one was given to me. But if you just take the various values of the fusion rate, this includes some data, I believe, on gamma rays, etc. But you can see this is the 4 orders of magnitude variation. The square boxes have to do with values presumably reported, and the crosses are limits above which it's claimed that the particles could not be observed. Charlie Bowman and John Moses were the head of the staff, but a very diligent, intelligent group put these together. Excuse me? X-axis. Oh. What's on the x-axis? I just viewed this as a panel. What is it? Huh? Paper numbers. See, I never even noticed it, you know. That's an irrelevant variable. I suppressed it. As a matter of fact, we should have suppressed it like that. Again, it's not the details of each one, but general range. Gammas and charged particles were either seen or not seen, as we said, at this general range, consistent with the neutrons. I think one of the most fascinating things I learned about was the observed, or claimed to be observed, neutron bursts. Questions of cooperative effects, of course, were raised. The average rate is clearly still very small, but one sees between 10 and 100, or maybe many more in some experiments, in very short time scales. Whether the fusion or what have you, producing one neutron, then catalyzes another, etc., due to local heating. Very unclear. The tritium buildup was another enormously fascinating issue to me. There have been many questions about whether this could be a contamination. There have been arguments no, back and forth, and I think within the next month or so we should probably know a lot more about this tritium issue, but I think it's extremely important. There were many fascinating and imaginative theory papers. What causes all of this? Well, if you look back at the usual expression for the rate of a reaction, which is a tunneling reaction, there's an attempt frequency in D2. This is the typical vibrational frequency of the molecule. And then a penetration factor, which written here as 2 times a quantity S over Planck's constant. S is the classical action. That is the integral of the momentum times position, which is the action. Now, you probably know this in the usual form, the square root of the effective mass times the difference between the potential and the incoming energy of the particle, or the reduced coordinate, when it hits the tunneling barrier. Suppose this classical turning point R0 is here, and we have to do an integral. One thing that really amazed me when I first heard about cold fusion was to do this integral, and I did it simply by setting E equals to 0 just to do it easily. So you have to do the integral of E squared over R for the potential times 2 mu, if you like, pull that out. The integral of 1 over the square root of R dr is very easy to do. That's the square root of R. I said, okay, where does that integral come from? Is it from the angstrom scale? Is it from the Fermi scale, 100 Fermis? Where is most of the, the difficulty to get tunneling in? Well, you see, it comes from the larger values of R, which I was really surprised. Most everybody knew that, but I didn't. So I said, gee, that makes it possible for screening or what have you for electronic motion to change the effective potential. Were it down on the 5 or 10 Fermi scale or 100 Fermi scale, there's not much screening down there. But when we're up on the 1/10 of an angstrom to an angstrom scale, where a lot of this comes from, it may be more possible. Well, there have been calculations going all the way back to Zeldovich and company for the D2. Recently, Kunin and Nauenberg have improved that, but the rate for just a free molecule for it to fuse, is something like 10 to the minus 65th, around that range. So it's equivalent to about 1 fusion per mass of the sun per second or per hour. It doesn't make much difference per year. It's all on the same scale. But that's a pretty small rate. Now the observed rate, of course, is not 10 to the minus 64th, but 10 to the minus 23rd. That is, it's about 41 orders of magnitude enhancement. The second thing that really shocked me was that this number is enormous, and yet it's only 2 or 3 sigma above the 1989 limit of most detectors. How was nature so remarkable in adjusting this enhancement factor to bring it a few sigma above the current detectors? Well, of course, when you lower the noise, as was done in some very beautiful experiments mentioned in the conference, the rate doesn't decrease, but it stays roughly the same. So maybe it's just an accident of nature. So that's one question. And the other question is, why is this enhancement factor essentially so insensitive to whether it's palladium or titanium? Why should 41 go to 41.3 rather than to 48 or 37? So it's this compensation effect, or whatever is going on, if everything is real, that again is, I think, really a great challenge. If you think about how big a screening factor, suppose you talk in terms of an effective dielectric constant. I realize the more standard way is to talk in terms of a bond length. How much must you change the bond length? Suppose you change the potential, however, by a screening in a dielectric. How how much must this be? Well, the dielectric screening must be about a factor of 9 in order to get this 41 orders of magnitude enhancement in the rate. Now you can say, gee, in a metal, the dielectric constant is infinite. What's the problem? Well, it's infinite for infinitely long wavelength. When you get down to 1 angstrom, it is more like a half, or so you can reduce the field by a half. When you get down to a Fermi, of course, you don't do anything. And that's the magic of the uncertainty principle. I remember a student in the nuclear physics class I had was talking about the angular momentum barrier, and he wrote L squared. I said, is that the right thing? I said, isn't it L times L plus 1? He said, oh, you can also write it as L times L plus 1. I said, which one's correct? He said, that's the uncertainty principle. Nobody knows. Theorists have a lot of ways of getting out of tough corners. Okay. Now, I think a very nice paper, just mentioned because it was unfortunately not able to be presented here. Both authors were away. It's being submitted to Physical Review Letters by Tony Leggett and Gordon Boehm. They claim that they have a rigorous upper limit to the fusion rate in solids and at equilibrium, and that's of order 10 to the minus 30th rather than 10 to the minus 23 or so. If this is in fact true, and from what I can see reading through the manuscript, it looks probably right, then it would suggest that one has more interest in looking at non-equilibrium phenomena. These bursting, the cracks, dendrites, fields, et cetera, maybe are more likely what's going on. They do say, however, the same arguments can be applied to the non-equilibrium case, but perhaps with a little softening of this, but don't say by how much. So that's an interesting question. Well, I certainly don't want to try to summarize what we heard. I think there were many, many papers which I feel I could study in great detail. But one thing I would like to suggest is the diagnosis by process of elimination, either on the physics or on the chemistry side, is extremely dangerous. I once had a doctor diagnose my mother as having cancer of the pancreas. You know, we're all quite upset, and my father bought a place to have my mother go to rest. And about a week later, they said, whoops, we made a mistake. Her electrolyte balance is off a little bit. You know, that is not a good way, because they had removed all possibilities except one that they happened to know about, and that was the wrong one. So I think one has to be enormously careful to make sure you have the smoking gun rather than trying to determine things from other causes. This reproducibility is crucial. Here I have a little picture. I am not an artist, but my daughter is, and she wasn't around, so this is the best I could do. Here we are started March '89. It was suggested that we have these two marvelous phenomena, chemistry-oriented perhaps, and nuclear physics-oriented, really intertwined here. It may well be that the paths will pull apart, but that doesn't mean that there's not a beautiful land that each of these two phenomena will evolve into, and we might even have meetings of historical significance in the future. My own prediction is this is probably the case. What is not shown here is that the materials in between will probably continue to connect these two sides, even if the phenomena themselves are not intimately connected. So that's a personal, private suggestion only. And finally, I would like to add to what Norman had to say about those we should extend our special thanks to Reed Jensen and Barbara Seitz and Kaczewski for helping us organize this meeting, particularly to Charlie Bowman and John Moses and his staff for putting together the database, which made my life early this morning much easier. To Sig Hecker and our friend Ray Kaczewski of DOD for their support, particularly chairs, participants, speakers, for an exciting meeting, and I thank you.
I wanted to just say one word of thanks to our chairs, Dr. Schriefer and Dr. Hackerman, whose work made this conference possible, and also the program committee for many hours of hard work.
That's all, folks. Yeah. Oh, Bob.